This conference will now be recorded.
All right, welcome to class number 3 of the SELDM for the fall of 2022. So right now we'll just do a short introduction to the hydrology within SELDM. So SELDM's a stormwater model that provides the concentration, flows, and loads, and the stream quality analysis for assessing the potential effects of runoff on receiving waters. So if we were in the classroom, this would be training module 3. So we've seen this diagram a couple times. SELDM uses this simple mass balance approach to calculate the flows, loads, and concentrations by storm event and by year. So it uses Monte Carlo methods, which means it uses random generation techniques to generate a bunch of hydrologic variables to look at what would happen in the stream over time. So as we see in this diagram, we get our upstream concentrations and storm flows. You multiply those together, you get your upstream loads. And from their highway site or urban site or say highway maintenance yard of interest, you get your concentration of runoff times your storm flow, gives you your highway runoff load. SELDM has a way to model BMPs to see how you can reduce those concentrations, storm flows, and loads. And then we just add the upstream loads together to get the downstream load. We add the upstream storm flow to the highway runoff or BMP storm flow to get that downstream storm flow. And when you divide the load by the storm flow, you get those downstream concentrations. We've looked at this diagram several times. So the diagram shows the components of upstream flow and highway runoff flow that combine to define the downstream flow statistics. So if you remember from last time, we have the physiographic and anthropogenic basin properties affect the upstream pre-storm flow and storm flows from the upstream basin and the highway site. So those are the latitude and longitude. The drainage area are used to identify stream flows to use to define the pre-storm flow. The total impervious fraction is used to calculate runoff coefficient statistics for the upstream basin and the highway site. And the basin length, slope, and basin development factor or imperviousness are used to calculate the timing of runoff from the upstream basin and highway site. So we get those two summations of flow from the upstream basin and the highway. And again, we just add them together to get those downstream flows for each event that SELDM simulates. So this will be just kind of a quick overview. If you really want to dig in deep, we have the 3 federal highway reports that's kind of set up the variables. They're all peer reviewed and it establishes the methods that we use. We also have we have a bunch of USGS reports that talk about the individual variables that we use to do the flows in SELDM. So we've looked at this document or this graphic a couple times. So SELDM has the graphical user interface with a series of forms. So we have our documentation forms and our site and region forms. Now, we put in our basin properties of the highway and the upstream basin to determine the hydrology of the sites. The ecoregion will give us precipitation and or upstream storm flow. And then we get into the hydrology forms where we specify or pick our precipitation, our pre-storm flow, and our runoff coefficients, which are based on the imperviousness. Or you can put in your own runoff coefficients if you have them for a given site. Then we get into water quality and then the BMP treatment and run the analysis. So SELDM uses the EPA definition of a synoptic runoff event. Synoptic storm events are defined by grouping hourly pulses of precipitation that occur within the minimum inter-event time. The precipitation statistics are calculated from hourly precipitation data for use in SELDM. So these graphs show the precipitation intensity in inches per hour on the vertical axis and time in hours on the horizontal axis. The schematic diagram is an example showing the process for lumping hourly rain pulses into these synoptic events. So each bar on the upper timeline, which is labeled hourly precipitation data, represents an 1 hour pulse of precipitation. The minimum inter-event time is used to either separate pulses into different storm events or to lump pulses within an event. So you can see there's these minimum inter-event time on this time axis. So we can see on the upper graph, these two pulses get lumped into one storm, but because the next pulse is after the minimum inter-event time, that gets lumped into the next storm. But when we go look at this other one, we can see that we had an event and then a time gap and then another pulse. Because that's less than the minimum inter-event time, that gets lumped together into that pulse. So each of the bars on the bottom timeline shows a synoptic event corresponding to the cluster of hourly pulses in the upper timeline. Each event has a duration equal to the time between the beginning of the first pulse and the end of the last pulse. Each event has a volume that's equal to the sum of the precipitation that occurs in all the pulses during that event. So the EPA definition of a runoff generating event has a minimum volume of 0.1 inches of liquid precipitation and a minimum inter-event time of 6 hours. The minimum event duration of 1 hour is a result of using an hourly precipitation data set. The minimum interval between storm event midpoints is a result of that 6-hour minimum inter-event time added to the midpoints of two 1-hour events. So this definition has been used by the EPA, Federal Highway Administration, USGS, and other federal and state water resource management agencies to define storm events. So SELDM uses the average number of storms per year to calculate the minimum number of runoff producing storm events to be generated in a given analysis. This graph shows the linear equation that we use to calculate the minimum number of storms with data points for each EPA rain zone and for stations with the minimum and maximum number of storms per year. So the vertical axis shows the calculated minimum number of storms. The horizontal axis shows us the average number of runoff producing storm events per year. The minimum number of events to be generated is calculated as 725 storms plus 17 times the average number of storms per year. So these coefficients were selected to balance the need for a sufficient number of storms to reach like stochastic convergence towards input statistics and the desire to generate a period that was comparable to the length of record for stream flow and precipitation in much of the country. So you can see on this graph that the minimum station is going to give us about 760 storms, and the maximum station in rain zone 15 in the Northwest is going to give us a maximum of about 2,250 storms. Sorry about the sneeze. So as I said on the first day, we're looking to generate between like 1,000 and 2,000 storms at most sites and roughly about 20 to 30 years of data, because that's what was roughly available for a lot of stream gauges and precipitation gauges. If we tried to simulate 10,000 records, it would, or 10,000 events, or, it would bloat the data files, and it would give you years beyond the available data, or, as we see recent shifts in data. And, therefore, it would, I guess the biggest thing of having too many events, it might give you more confidence in the input data, in the output, than you really have in the input data. So as we discussed on the first day, you can select precipitation statistics by EPA rain zone, by ecoregion or by the 2,610 hourly precipitation data stations that are preloaded into SELDM. So this map shows the ecoregions, rain zones, and the location of all those precipitation data stations. We picked stations that had at least 25 years of data during the 1965 through 2006 period, and the latitude and longitude of the precipitation data stations are used to rank the stations by proximity to the site of interest. So as we talked about on the first day, if I'm out here in Nevada, in the middle of Nevada, I can choose statistics for rain zone 11. I can choose statistics for the basin and range ecoregion, or if I'm in this area of Nevada, I could choose the average or median of 1 to 3 sites in this area. So the benefit of drilling down to specific sites is, in theory, you get more representative statistics. The downside is that you have to do a little bit more work to make sure that the one or several that you choose are actually representative of your site of interest. For example, if you're in Carson City, Nevada, it's a very dry area, but you go just a couple miles over the mountain range and it's a very wet area in the Lake Tahoe Basin. So the closest precipitation gauge may not be the best. Same thing with the stream gauges. Let's see. So what we look at is, in the hydrology of the system, we're looking at pre-storm flow and then upstream runoff. So as this diagram indicates, the pre-storm flow times the runoff duration is added to the upstream runoff to calculate the upstream total flow used for dilution calculations. The amount of dilution depends on the amount of pre-storm flow and upstream runoff that occurs while the highway runoff outfall or the highway runoff BMP outfall is discharging to the stream. In SELDM, the pre-storm flow is held constant and we use a basic triangular hydrograph. So in SELDM, you don't get to dilute your highway runoff into this total upstream hydrograph. You only get to dilute it into that concurrent hydrograph. But if you put a BMP in that stretches out the discharge duration, you get more and more of that combination of upstream runoff and upstream pre-storm flow. So pre-storm flow is not necessarily pre-storm base flow. So we use the mean daily flows to estimate what your pre-storm flows may be. So on this graph, we see the blue line is a hypothetical set of hydrographs over time. The gray bars that drop down from the top line are different precipitation events, and the gray circles are the points at the beginning of runoff generating events. So we could see in this first event on the left, that might be what would be called a base flow. And then we see we have a small storm that might return to base flow, but then we have a larger storm and a storm quickly after it. So the pre-storm flow for this third event would actually be in the tail of the previous event. And then again, we have stream flow recession, and you have another event, small event starting, but then you see that we have these large events. So in stream basin, it can take days for a storm flow hydrograph to move by. And as we said, if we're looking at hourly precipitation flow statistics, you could have 3 1-hour storm in a 24-hour period. So very often your next storm flow hydrograph occurs on the back of a previous storm. So SELDM uses 4 statistics to model pre-storm stream flow. The other statistics are just used to assess hydrologic similarity. So what does SELDM use? It uses the fraction of the daily mean stream flows recorded as zero flow. Now, if you have a perennial stream, that's going to be 0. If you have an intermittent stream, that's going to be somewhere on the order of, 0 to the number of storm events per year. And then, if you have an ephemeral stream, your pre-storm flows could all equal to 0. So the fraction of daily mean stream flows might be 1. So every storm event occurs, you may well be, starting with 0 base flow. So or 0 pre-storm flow. So the only flow in that channel would be runoff from the highway and runoff from the upstream basin. So in SELDM we do area normalized flows. So it's in cubic feet per second per square mile. So 1 cubic foot per second is enough to fill an Olympic-sized pool in 1 day. So we can fill 1 pool per day per square mile at this rate. So, I just kind of use this graphic because sometimes it's hard to think in these units, like, what am I getting here? So for each CFSM, you are, basically, like I said, it's 1 pool per day per square mile. Looks like a lot of water. So like precipitation, you can select streamflow statistics by region or by using values from one or more of the 2,783 stream gauges that are preloaded into SELDM. So again, if I go to this area in Nevada that has, we could see that, we don't use rain zones for stream flow because that doesn't quite make sense. But if I'm here in Nevada, I can use the average or median stream flow from the basin and range ecoregion, which is this pink polygon, or I can use the average or median of these 4 or 5 sites here near my site of interest. But again, when I'm looking at these particular sites, I want to look to see which one might be most representative of the site I'm looking at. And I guess a trick to see how important that choice is when you're in SELDM and you go to specify nearby sites of interest, you can look at the variations in the statistics that come up on the selection form. If all the nearby sites have similar statistics, then it's probably not as critical to pick the exact one. But if you see stark differences among nearby sites, you might need to be more careful about which one you pick or which couple you pick. Now there's 2,700 and something stream gauges already built into SELDM. Back in 2017, we did a study with Federal Highway and the USGS Stream Stats group. We did statistics for 18,122 USGS stream gauges that had 1 or more years of record. No, actually it was 3 or more years of record during the 1901 through 2015 period. So you can go to Stream Stats in any state of the country, whether or not it has a statewide Stream Stats application. And if you just drill down, you see the triangles indicating it's a stream gauge, and you click on it. And if it had 3 years of data in 2015, we calculated statistics for it, and those statistics are available for you. So you can use the ones in SELDM, or you can enter your own statistics, and you can get those statistics, by looking around at a nearby stream gauge. So SELDM uses runoff coefficients to translate the precipitation volumes into runoff volumes. So it uses the total impervious area to calculate those runoff coefficient statistics. The total impervious area is defined as the proportion or percent of contributing area occupied by anthropogenic impervious surfaces, which primarily consist of pavement and roofs. The total impervious area can be expressed as a fraction of 0 to 1 or the percentage 0 to 100 of total drainage area in the literature. SELDM uses the impervious fraction to define the TIA 0 to 1 of the highway site and upstream basin. We did that because if you're going from 0 to 100, and somebody puts in a 1 thinking they're getting 100, that can be confusing. But if you limit them to the 0 to 1 range, it's harder to misspecify the actual imperviousness you want. So this is that schematic of a diagram of the basin in map view showing our selected components of the total impervious area. The total impervious area is used to define those runoff coefficients. So, this is just our basin in map view, and we can see we have our roads, roofs, parking lots, etc. So the total impervious area estimate is used in SELDM to calculate runoff coefficient statistics. This graph shows the average runoff coefficients on the vertical axis and the impervious fraction on the horizontal axis. The dashed line is the regression relation developed for estimating the average of runoff coefficients at highway sites, which are shown as triangles. The highway site regression equations were developed with data from 58 highway sites across the country, with 9 or more storm events that had drainage areas ranging from 0.05 to 106 acres and total impervious fractions from 0.27 to 1. The two solid blue lines are the two-segment regression model developed for estimating runoff coefficients at non-highway sites, which are shown as the white circles. The non-highway regression equations were developed with data from 167 sites across the country, with 9 or more storm events that had drainage areas ranging from 0.005 to 93.5 square miles and total impervious fractions from 0.001 to 0.994. For these sites, the mean runoff coefficient increases gradually with imperviousness below a fraction of 0.55. The slope of the average runoff coefficient equation increases above this breakpoint for these sites. The breakpoint between segments is shown as that vertical gray line. So some sites have average runoff coefficients that seem too high for the measured total impervious area. These sites may be showing the effect of natural impervious areas such as bare rock, open water, or saturated wetlands. Sometimes also these values are affected by the location of the imperviousness. So if you're in a basin that's low impervious, but all the imperviousness is perched on the edge of the stream, you're going to get a bigger response than if that imperviousness was spread out over the whole basin. So within the SELDM interface, you can use these equations as the first cut. But if you know something about your stream or you have, data at your stream, you can use professional judgment to vary those values. I would say that if you look at these, we found that if you go from 0 to 1, there's not or from 0 to 0.1, which is 10%, there's not a huge difference in the regression value. So we see that, below that 0.55, changes are gradual. So the good thing about that is you don't need to precisely define your imperviousness. Although, in some states with, that have imperviousness in stream stats, it's really easy. In other states, you might have to use other measures like road lengths or population density, which gives you a fuzzier answer. But the good news, as we see here, is that you don't really need the exact number. So this graph shows the populations that might be generated with our runoff coefficient statistics using, the different impervious fractions. So the selected statistics calculating using the TIA values are used to generate the population of runoff coefficients. This graph shows the runoff coefficients generated for the upstream basin using the equations developed for non-highway sites. The runoff coefficients vary from 0 to 1 on a linear scale on the vertical axis, and the exceedance probabilities vary from 0 to 99.99 on a nonlinear probability scale on the horizontal axis. Again, this is that weird axis that they stretch out the extreme values, and a lot of the, the center of the distribution is all kind of packed together in the middle. So the alternating blue and yellow lines show the population of runoff coefficients generated for impervious values between 0 and 100%, on a 10% interval. So the mean coefficient increases gradually with imperviousness below an impervious percentage of 55. So the lines for the low TIA values are closely spaced. So we can see down in that area, you don't need to be super precise because the runoff coefficients aren't going to change by a heck of a lot, with adjacent numbers of impervious. So the standard deviation of the runoff coefficients does not change much with respect to the impervious value. There's not large differences in the slope of these lines that you see on the graph, and the skew of the runoff coefficient decreases with increasing imperviousness. So the lines representing the different runoff coefficient populations transition from strongly concave up, so you can see it kind of looks like a bow facing up, to kind of a straight line when you get to like a total impervious area of 80%, and then kind of weakly concave down by the time you get to an impervious area of 100%. So this graph shows one stochastic realization. So we ran all the same values, but just with different imperviousness. However, you're not going to get these exact values at your site, but you're going to get something similar if you just copied the analysis and ran SELDM and varied the imperviousness as it goes up. So when we were designing SELDM, we wanted it to reflect how data looks in the real world. So we looked at, if you look at like the curve numbers that EPA uses for several of their models, you have the antecedent wetness. So we looked at a lot of the literature and available data to try and figure out how can we simulate the effects of, antecedent wetness on runoff coefficients. So SELDM, through that process, looking at different variables, SELDM has the provision for correlating the upstream runoff coefficients with the pre-storm stream flows. We found that when the pre-storm upstream stream flows were higher, that tended to indicate that the basin was wetter. So runoff coefficients would be higher in a wetter basin. So SELDM has this capability because in theory, higher pre-storm flows indicate the wetter antecedent conditions that generate those higher runoff flows. So data from the runoff coefficient data set that we use seem to support this assumption. The graph is a probability plot showing the percentage of the 43 sites with 7 or more paired base flow and runoff measurements that have non-parametric rank correlation coefficients less than or equal to the specified value. So again, this is a probability scale, and this is the percentage of sites that had these rho values less than the value. So the rank correlations are on a linear scale on the vertical axis, and the percent less than or equal to a given value is shown as the probability scale. The calculated value is shown as the black circle, and the vertical yellow lines show the 95% confidence for each value. And that's just a function of the rho value and the sample size. So data sets with few storms have large variation above and below the correlation coefficient, and ones that had many storms had these narrow correlation coefficient bands. So doing this analysis, we saw that most of the sites that had a lot of samples and therefore were, we have better confidence in what the actual correlation between the pre-storm flow and runoff coefficients might be. Those runoff coefficients or those correlations are within this band of 0.5 to about 95. So in SELDM, we made the default value 0.7. And what that says is the runoff coefficient is not going to be in lockstep with the magnitude of pre-storm flow. It's just going to be when pre-storm flows are higher, you tend to get higher upstream runoff coefficients. And again, it's a stochastic model, so things, it's not literally a roll of the dice, but there's, you know, a computer roll of the dice going on that's matching up these values. And as I said, we did this because SELDM is behaving like what we would see in the field if we had field data at a site of interest. So then we also had to address the problem of, you know, if we have a highway site, or more likely if we have a developed site with some imperviousness, how are the highway runoff coefficients going to vary with the upstream runoff coefficients? So what we did is, no one's collected this data, but we consulted with a number of national experts on this, and we kind of came up with this method by which we have the highway site imperviousness from 0 to 1, or that's 0 to 100 on the vertical scale, and we have the upstream basin imperviousness from 0 to 1 on, or yeah, 0 to 100 on the horizontal scale. So if the upstream and highway are both completely paved, so both have an imperviousness of one or 100%, those two surfaces are going to behave the most similarly. So we could see that it's our maximum here would be a correlation of about 0.98. But you know, how often do you have a fully impervious upstream basin? So as with a highway site of 100% impervious, as the upstream basin goes from impervious of 100% down to 0, you get less and less correlation until, you know, when you have 0% upstream impervious basin, you get a correlation of about 0.375 between the runoff coefficients. And, you know, similarly, if you have a highway site with an imperviousness of 0 and a upstream basin with an imperviousness of 100%, you get that 0.375. So you can see, if you think about this as like a topographic map, the ridge line from the maximum value goes diagonally down this way. So the maximum local correlation you get is when, you know, the imperviousness of the highway and the upstream basin are equal, and you get less correlation as you go to lower imperviousness, because, you know, you have variations. If you had two fully impervious areas in a watershed, you know, the antecedent wetness is going to affect those differently. I know this gets a little complex. I guess you don't need to know the details of this, just you could be vaguely aware that the upstream basin and the highway site are going to, at some level, tend to behave similarly for a given event based on, you know, the theory that, you know, antecedent wetness is going to affect runoff coefficients. So as we discussed on the basin properties, the basin length and mean basin slope determine the timing of runoff from the highway and upstream basin. This is a schematic diagram of a basin with a map view and a cross-section showing these physiographic basin properties. So we use this representation for the highway and the upstream basin. So the basin length, also known as the main channel length, is the total distance in miles from the point of interest to the highest point on the basin boundary following the main channel route. The basin length might be longer than the straight line length between the point of interest and the selected point on the basin divide if the channel is sinuous, which is more likely to occur for a river than a highway. The mean basin slope, also known as the main channel slope, is the average slope of the main channel of the stream upstream from the point of interest. The mean basin slope selected for SELDM is known as the 1085 slope because it's calculated by determining the locations and elevations of points at 10 and 85% along the main channel from the point of interest to the basin divide, then dividing the difference in elevations in feet by the distance in miles between these points. So it's an easy slope to calculate, and research has shown that this is a highly representative slope. In predicting high flows, it has a better response rate than other measures of basin slope that were tested. So this hypothetical figure shows the importance of modeling the timing of storm flows within a runoff event. The diagram on the left shows the runoff hydrograph from a basin upstream of a site of interest and those two potential hydrographs from the site of interest. The hypothetical graph on the right shows the cumulative percentage of total upstream storm flow that occurs as the storm progresses. The diagram shows two potential runoff hydrographs from the site of interest, one with a short duration, so that would be duration 1, and the other with a longer duration, duration 2. So we can kind of imagine this might be the highway runoff, and then this duration 2 might be if you put in a BMP that slows down that outflow. So, you know, this could be a detention pond, or it could be as simple as using grassy swales to route the runoff instead of sewer pipes. So that might slow the discharge of runoff. So in this example, and this is a purely hypothetical example, if we have this short, sharp highway runoff hydrograph, we can see that given this upstream pre-storm flow and upstream runoff in the triangular hydrograph, we would only get to, say, duration 1 here. So in this hypothetical, purely hypothetical example, for the highway runoff would only get about 15% of the total upstream storm flow during an event to use as dilution. However, if you can stretch out that hydrograph using a BMP, or instead of using, you know, stormwater pipes, you use grassy swales to slow down the flow, you could get up to that duration 2, which in this hypothetical example is 55% of the upstream runoff. So again, you know, this is just a schematic diagram and a hypothetical example. The actual values that you would get would depend on your BMP that you select, and you know, it varies from event to event stochastically. So as we mentioned, SELDM uses this triangular hydrograph to simulate the timing of runoff. So this schematic diagram shows the variables that define a triangular runoff hydrograph. So this is just a standard triangular hydrograph that, you know, from similar to TR55 and even a lot of the complex, seemingly complex basin models still use a triangular hydrograph. So the total duration of the hydrograph from the beginning time to the end time is known as the base time. So that's this TB variable. There are two parts to the triangular hydrograph: the rising limb, that's the upward, you know, before the peak, and then the falling limb after the peak. So the duration of the rising limb is known as the time to peak. The duration of the falling limb is the recession time. The base time is the sum of the time to peak and recession time. So three basic variables: the duration of rainfall, the basin lag time, and the hydrograph recession ratio can be used to derive the timing of a triangular hydrograph for a given storm. The basin lag time is the fundamental timing variable for a given site. The basin lag time is defined as the time between the center of mass of the unit rainfall and the center of mass of the associated runoff. The basin lag time is commonly defined as a characteristic of the drainage basin rather than a characteristic of a storm event. And SELDM, the basin lag time is calculated using that main channel length, the main channel slope, and either the basin development factor or the percentage of total impervious area. So this is our basic hydrograph. And as I said, the length and slope give you this basin lag time, which is from the midpoint of the storm to the centroid of the runoff hydrograph. So as with other things, we did a lot of research to try and get, you know, good numbers built into SELDM so you wouldn't have to do a lot of work to get them. So this graph is the scatter plot showing the basin lag time data from 896 sites across the United States, and regression equations developed using the basin lag time, the basin lag factor, which is the length over the square root of the slope, and the total impervious area in percent measured at these sites. So the axes on these graphs are the same, are the basin lag time in hours on a log scale from 0.01 hours to 200 hours. And on the bottom is the basin lag factor, again, the length divided by the square root of slope from 0.001 to 100. we can see that for a given value of length and slope, increasing the total impervious area from 0 to 100% reduces the baseline by almost an order of magnitude. The total impervious area may be used to calculate the basin lag time with the equation shown on this graph if you put a -1 in for the basin development factor in SELDM. As with the basin development factor, we should try to derive the most accurate and defensible TIA estimate as possible, but we can see, when imperviousness are low, and on this graph, imperviousness starts at 0 on the top and goes to 100 at the bottom. So the time goes down as imperviousness goes up. But you can see until you get up to an imperviousness of about 50%, that those blue and yellow lines are right on top of each other. So at low impervious values, you don't need to get the exact right imperviousness to get that estimate of your basin lag time. And we can see, yes, the data for these 895 basins have a pretty good amount of scatter. That's to be expected for a nationwide data set. And again, when you look at SELDM, you can use professional judgment to vary the variables to kind of get the basin lag factor that you expect if you have on-site data. All right, so we have the basin lag time, which gets us the front end of the storm event, but then we need to get the recession ratio to get the full timing. So what we did is we've done a number of studies where we look at the recession ratios from any storm to fit a distribution. So the recession ratio isn't fixed. The basin lag is fixed, but the duration of the precipitation event is different. So that affects where the centroid lands. And then the falling limb of the hydrograph is a random variable in SELDM. So the final step for defining the statistics for modeling storm flows in SELDM is to fit a distribution of the recession ratios. So in this graph, the plotting position percentile is on the horizontal axis, which is a probability scale. The recession ratio values are on the vertical axis. The numbers in the upper right are the minimum, most probable value, and maximum values for the best fit distribution. So a sample of recession ratios for 20 or more storm event was used for each station that we analyzed to build a robust sample of recession ratios. We did a least squares fit to kind of come up with this distribution for these data, and the symbols show the plotting position of the recession ratios. So what we see here is that the ratio of the falling limb for the rising limb in this case goes from about, 1.3 to, of the data that we looked at, to about 2.4, but then we fit this distribution and we can say it goes from about 1.03 to 1.95, because 20 events isn't 2,000 events, so we needed to fit a distribution. So in 2012, we calculated these for 41 stream gauges across the country. This is a box plot showing the values for the maximum, most probable value, and minimum. And so we can see that there's a good amount of variability, but we didn't find geographic variability, and we didn't find any good basin characteristics that would explain the recession ratios that we got. So basically this shows, since then, for a study in Southern New England, we did a number of gauges in, additional gauges in Southern New England. In North Carolina, they did about 20 or 30 gauges since we did the 2012 study. And in Oregon, they did 2 studies where they did a handful of stream gauges out there. And what they find is that, all in these different areas of the country, the recession ratios are still in the ballpark. That's kind of similar to when you look at the physiographic characteristics of drainage basins. even in different climates, you kind of find that for a given drainage area, the length and slopes are similar. So one could see that, that maybe these recession ratios aren't site specific, they're more, physiographic in nature. So I guess when we come back to this, what we just talked about was that SELDM generates the precipitation events, the pre-storm flows, runoff coefficients, and these basin timing variables, so that we get the upstream flow. We get the highway runoff flow or BMP discharge flow, and we get the upstream flow that's concurrent to those flows. I guess when I designed this graph, I probably should have put the highway on the left and the upstream basin on the right. I guess I was thinking spatially from upstream to downstream. All right, let's see, I don't know if I should pause and ask for questions or kind of roll through water quality and then take questions at the end. I guess if somebody has a question, feel free to chime in or put something in the chat before I roll on to water quality. So I know that was a lot of information. Again, we quickly covered a lot of information, the precipitation, stream flow, hydrology, runoff coefficients. We put a lot into the design of SELDM, but kind of the umbrella of it is very simple, but you get down to the nuts and bolts. We tried to make SELDM represent real world conditions as best as we can within the uncertainty of available data. And so that you could, if you remember from the first class, you could run SELDM within half an hour to an hour. Once you get good at it, you can, I can put in an analysis and run it in, 10 or 15 minutes. So the idea was to get good, solid planning level analyses without spending a lot of money putting together a model and calibrating it. Basically, you calibrate SELDM by putting in good statistics. I worked on an HSPF study that covered the Pawcatuck River Basin in Rhode Island, and we were trying to couple groundwater and surface water flows, but just doing flow in that basin cost $2 million in 5 years. I mean, we did a lot of work to nail down a lot of hydrologic variables, but in the end, really at any given highway crossing in that basin, there was still a lot of uncertainty as to what the flows would be, never mind what the water quality would be. So you can spend a lot on very detailed models, but unless you have the data to feed those models, you get very uncertain answers. That's why we spent a lot of time doing a lot of these hydrologic statistics for you. All right, I am just going to give a quick overview of water quality modeling in SELDM. So our learning objectives for this is to realize that water quality is complex. Good data requires characterization in time, space, and with hydrologic variability. The SELDM webpage provides the material you need for further study, and the highway runoff database indicated the importance of different constituents in SELDM models. SELDM simulates water quality by using random water quality, dependent water quality, and transport curves. For the highway, you just have random or dependent. For the upstream basin, you get random, dependent, or transport curves. So typically when we had an in-person class, I would give you a CD-ROM with the reports on background water quality from USGS, our project, and Federal Highway. I'll send everyone links to these reports, the ones that are available online. So if people want to do a deep dive, they can, learn more. You're always, once you take the SELDM class, you got a golden ticket to always contact me at any time in the future to ask me a question. So as we're looking at this mass balance. So what we see is that we need representative statistics for the upstream and highway runoff concentrations. So this shows that schematic. On the left, we have a picture of a stormwater sampling station for monitoring. I believe this was the Charles River upstream of the Watertown Dam. So we were getting real-time water quality, well, near real-time water quality there to get those upstream concentrations. And then this picture over here is a highway runoff monitoring station. You can see the guardrail there. So again, we're getting these event mean concentrations based on an auto sampler. Um, highway runoff is more common. It's very uncommon to get event mean concentrations or high intensity auto sampling in receiving waters. So that's why we went with the transport curve option, which I'll explain in a few slides. So again, to get these upstream loads, we need an upstream concentration and storm flow. We have these highway concentrations and storm flows, and we add together the loads, and we add together the flows and divide to get those downstream concentrations. There's only one study I know, and that was in North Carolina bridge study, where they looked at upstream highway runoff or bridge runoff and downstream, and even then only for a few storms. So in most places we're looking at, we don't have data available. So we have to use available data and apply those to the sites of interest. For example, in southern New England, we put road crossings into stream stats, and we found that there was about 10,000 road stream crossings in southern New England, and we had only about 10 data from about 10 highway runoff monitoring sites, and only about 80 stream sampling stations that we were able to use, and that was only for some of the most commonly measured water quality constituents. Once you got into some of the exotic water quality constituents, the number of samples and the number of sites drops precipitously. Okay, as we mentioned, SELDM has three approaches for modeling water quality. We have random, transport curve, and dependent. It's kind of hard to represent a random runoff, concentration. So I guess what I tried to represent here is a box plot. You think of a box plot as just showing kind of a random population. So in this graph, this is from the Massachusetts Highway Runoff site. We see total copper concentrations in milligrams per liter on a log scale on the vertical axis, and on the horizontal axis is not a numeric scale, it's just kind of a group scale, but we're showing the average daily traffic in vehicles per day. So you can see that, at our minimum site, we have 26 samples at 3,000 vehicles per day. And we see that the average total copper concentration at that site was about 10 milligrams per liter. You can see there's kind of a general trend upward as we get higher and higher traffic, but it's not very marked. But then you can see these last two sites, we go from almost an order of magnitude jump, and that's this site here at 154,000 vehicles per day. That's in on I-495 outside of Boston. So if you're driving down this road, look left and right, you think you're in the forest. And this is I-93 in Boston, and you can see there's this huge jump in concentrations. And when you look around on I-93, you're basically kind of in the urban area of Boston. So we have data that suggests that it's not all just average daily traffic. It's kind of the background contamination that can urban development that can affect the highway runoff quality. So this is a schematic diagram that we're trying to demonstrate how we generate random values. So the vertical axis here are uniform random numbers that get generated in SELDM. So the horizontal lines are just example lines or example values generated near 0.5 and near 1. So we can see that on the horizontal scale, they are parallel. The yellow line that goes from -3 to 3, it's kind of an S-shaped curve. That's the function that converts these uniform numbers to normally distributed numbers. And so we can see how the numbers that are fairly equally spaced near 0.5 get a standard deviation of about 0. But as you get up to the extreme values, because the shape of the normal distribution, the numbers get spread out, more than ones near 0.5. So to get the concentration, we have our average concentration plus the standard deviation times these randomly generated normal numbers, which are shown here as Ki. So as we mentioned, we do this in log space. So that's the average of the logarithms of concentrations times the standard deviation times this normally distributed random number, and that generates our population of values in SELDM. So this graph is a probability plot of the highway runoff data from the actual site and theoretical distributions. So these have a mean of -1.05 in log space and a standard deviation of 0.423. So because it's -1.05 in log space, that would be a concentration of about 0.1 milligrams per liter. So the vertical axis on this scale shows the total phosphorus concentration on the log scale, and that's back in milligrams per liter. The horizontal axis is again one of those probability plots showing the risk for exceeding a given highway runoff value. The theoretical log normal distribution, so that's with a skew of 0, is this green line. So on a probability plot, a log normal distribution would plot as a straight line. And then we can see that we have skews going from 2 to -2. And so with a positive skew, you have concave up distribution, and a negative skew, you have concave down. So if your water quality skews are positive, you're going to get much higher values on the high end, and it's going to kind of plateau on the low end. And if you have large negative skews, it's going to be the opposite, whereas you're going to get very low concentrations, and it's going to kind of plateau on the high end. So if you look at these gray dots, you can see that there's a slight downward curvature, so it's kind of concave down, and the best fit distribution is this, over the long term, is this, I guess, what would you call that? Purple, or it's not quite red. I should have picked a color that I know I can identify, but you can see that's the theoretical value that we get, and then the gray values are the actual highway runoff that we measured. So as I said, when you're quote unquote calibrating SELDM, you do that by putting in representative statistics. So if we're going to model a site in SELDM, we can calibrate the highway runoff quality by looking at variables such as the average daily traffic, or as we saw in Massachusetts, the surrounding land use. So in this case, this is values. This is a graph from our Massachusetts Highway Report. We see suspended sediment concentrations on the vertical scale from 10 to 1,000 milligrams per liter. And then if we look at that imperviousness in percent within a 1 mile radius, you can see that as the surrounding imperviousness goes up, you have increases in total sediment. And again, you can see here that this large circle with a surrounding imperviousness of about 30% is that I-495 site. And if we jump up sediment concentrations by about an order of magnitude, this is that I-93 site in Boston. So the urban highway is a lot dirtier than the loop road, even though you can see from the diameter of the circles that the average daily traffics are about the same. And you can see, although there's kind of a trend in terms of lower concentrations with smaller traffic, that maybe for suspended sediment, we can see that, it's probably a combination of average daily traffic and surrounding imperviousness. So in response to this, we're going to be putting the surrounding imperviousness for many of the sites into the highway runoff database. So people will be able to assess this as a variable going forward once they get their statistics. Now, SELDM does those random concentrations. It's kind of easier to show these dependent quality relations. So a dependent quality relation is basically a regression equation with a random variation around the line. So SELDM generates a random value for one water quality constituent. So that's like Xi. So that's our X values. Let's say that's suspended sediment is very inexpensive to measure. When you get to metals in organic chemicals, they're more expensive. Well, metals are a little bit more expensive than sediment, but then you go to organic chemicals and they can be orders of magnitude more expensive to measure. So there's less data for those constituents. So the idea of using a dependent quality relation is if you have limited data that you can come up with a relation between two variables, and you can use a larger data set, you might get a better answer than if you just had very few samples to generate a random relation. So I know out on the West Coast, a tire chemical 6-ppd or 6-ppd quione, if I'm saying it right, is very important for the fish mortality. And so this is an organic chemical. I think they're on the verge of getting an approved method to do the analysis for the chemical. So that means there'll be a lag time of a couple of years before you get a lot of great data. But we know historically that there's a lot of zinc in tire treads. So, hypothetically, we could use total zinc in to estimate 6-ppdq or 6-ppd concentrations in runoff. And zinc is going to probably be a lot cheaper to analyze. And, historically, we've got 50 years of zinc measurements in highway runoff. We have thousands of total zinc measurements, but perhaps, I'm not sure I think Washington has a few. They did a BMP study, so there might be some stormwater event mean concentrations for 6-ppd. So this would be a case of where you have these random variables. You'd use sediment to estimate 6-ppd, or the same thing can be said for a lot of polyaromatic hydrocarbons. If you have these expensive constituents, you can predict them from more measured constituents. So to do this, we generate this regression line. So it's an intercept plus a slope times the concentration of the thing that you have a lot of data for, but it's not going to be in lockstep. So we get that random variation around the line. So we use this kind of semi-deterministic method. From a sediment concentration, you get the line, and then the stochastic part adds noise or cloudiness around the line. So that the values that you generate will be this point cloud. They won't be like on this right on the line. Now, the third method that we use for upstream water quality is known as a transport curve. A transport curve is a regression relation between stream flow or upstream flow and a constituent of interest. What we found is different constituents, like sediment-associated constituents, tend to rise with increasing flows, and things like dissolved constituents that may be from like groundwater contributions tend to be diluted by increasing flows. Or often, if you have like an upstream wastewater source, storm flows are gonna reduce or dilute those upstream wastewater sources. So what we get is we have this upstream storm flow on this graph is from 0.1 to 100 cubic feet per second per square mile. And then we have a log scale of total phosphorus on the vertical axis. The blue circles on this graph are the actual data points from Sasko Brook in Connecticut. This was an example site. And this 0.1 milligram per liter is the receiving water standard. So what we did when we analyzed these samples, we found a 2-segment curve. So at base flow, we found that the concentrations were about 0.02 milligram per liter with random variation above and below that point. So in this stream, when you don't have runoff, outside of a storm event, you just kind of have random variation in total phosphorus. But then as flow increases, you're getting larger and larger flows. What's happening is you're getting storm flow into the channel, carrying sediment and, increasing total phosphorus. But also as the flows get larger, they kind of tend to mobilize sediment and phosphorus from the beds and banks. So that's why we kind of see this upward trend in the water with increasing flow. So the blue lines were our data, the yellow lines are regression equation, and these gray dots are the results of a SELDM analysis. So to do this, we do step 1, we plot our data with stream flow in cubic feet per second per square mile. And we do that so that we could use the transport curve from one site to estimate water quality at a different site with a different drainage area. So we generate that regression equation. In this case, our segment 1 has 0 slope. It's 0.02 milligram per liter. And then our segment 2 is a regression equation in log space. So it's 0.019 times the flow to the 0.44 power. And then when we use SELDM, we add that random variation back in. And what we do is we use the random variation in the original data to give us the random variation that we get. So the data sets that SELDM create will look like the data sets that exist in the real world at the measurement site. So this is another example of dependent water quality relation. So this graph shows suspended sediment in milligrams per liter on the vertical scale and total suspended solids in milligram per liter on the horizontal scale. So USGS has shown that total suspended solids is not a good representative of the actual suspended sediment, and that's because the suspended solids method just can't capture larger particles. So in this case, we see that as the suspended solids increase, that's when you're mobilizing more sediment in the sample and you tend to get larger solids. So TSS underestimates the actual suspended sediment. So we come up with this relationship. Now, why would we do this is like in highway runoff, there's 50 years of TSS measurements because TSS was selected, because TSS is good for measuring wastewater treatment plant out effluent, but it's not great for stormwater. But because that was a regulatory constituent for wastewater treatment plants, it kind of got co-opted for use in the stormwater realm. So we may have a lot of TSS values, but if we're actually looking for suspended sediment concentrations, we would use, we can use this large pool of available data with a limited pool of concurrent data to estimate what would go on for SSC. Similarly, here's in-stream. The dependent quality relations can be used for something that's easy and inexpensive to measure to predict the hard or expensive constituents. So in this case, we could see suspended sediment in milligrams per liter on the vertical scale in a log scale from 1 to 10,000, and turbidity from an in-stream sensor in, I forget what NTUs are, but that's from 1 to 10,000 on the horizontal scale. And so this is an actual site from Sedgwick, Kansas. And what we can do here is with the real-time record of turbidity, we could get flow weighted event mean concentrations in that stream, and we can develop this regression equation to get suspended sediment from turbidity. And we can use it as if we've got this huge data set. And in this case, this was their original data, and the points labeled A, B, and C were obvious outliers. And when they looked at that data, they were able to identify that, yes, there was something wrong with that data at the time. So, like I said, this is something where you have a lot of measurements where you're trying to predict where something that you may not have so many measurements because it's either hasn't been measured a lot or because it's very expensive to measure. Okay, the last part of simulating water quality in SELDM is using the downstream pair. So what the downstream pairs methods in SELDM allow you to do is it allows you to come up with different combinations of highway runoff quality and upstream runoff quality and pair those up to get different answers for the different combinations. So this is a schematic diagram. We have our highway runoff quality. We have 3 potential lead values. We have lead 1, lead 2, and lead 3. That might be, let's say, a low ADT rural site is lead 1, a mid ADT suburban site is lead 2, and a ultra urban site is lead 3. So we can simulate those 3 leads. And then if we have our upstream water quality is this upstream lead 2, so we use 1 upstream water quality estimate. And what we do is we're saying we're going to simulate these without a BMP. So what we get is we get 3 downstream definitions or 3 downstream outputs. We've got the highway 1 and upstream 2, highway 2 and upstream 2, and highway 3 and upstream 2. So this diagram just shows we're pairing them. So in this example, we're not doing downstream, we're not doing a BMP, and we're not doing this adverse effect ratios. So if we were interested in the potential effects of BMP, what we would do is we'd generate 2 downstream pairs. In each case, let's say we're using highway lead 2 and upstream lead 3, and then you can see we're feeding each one into a downstream pair. One has a BMP and one does not have a BMP. That's most commonly what we're doing. We're simulating a pair of constituents with and without a BMP, or in the same run, you can do multiple pairs with and without a BMP. So if we choose this route, like I said, we get 2 downstream definitions, the same upstream and highway, and just with and without a BMP, but we're not looking at this adverse effect ratio. I won't talk about the adverse effect ratio today because people barely do it if they do it at all. Basically, the adverse effect ratio is that fraction of the constituent in the water body that may cause a problem for your species of interest. For example, back when copper was the highest priority constituent, when they did more and more research, they found that they used a bioligand model to find that only a small fraction of the total copper is actually attacking the organisms of interest. So your adverse effect ratio would be, let's say for copper, the ratio of ionic copper to whole water copper. And that's, sediment associated, filtered, and colloidal associated copper. All right, I said I wasn't going to talk about it, then I did, so I apologize for that. It kind of gets complex. If people are interested in doing it, it's best if we get together and talk about it in detail. So in this training, hopefully we learn that water quality is complex. Good data requires characterization in time, space, and with hydrologic variability. Unfortunately, nationwide, there's not a ton of good data out there. We need more highway runoff. We need more upstream water quality. We'll provide materials for further study. Basically, I'll send you guys a list of reports for those who want to dig deep. There's a number of constituents that have been measured. You can look at the highway runoff database. It will indicate the perceived importance of different constituents. So you can kind of see, I should say the historical importance. You can see a lot of metals and a lot of sediment in the highway runoff database. So you can tell those were of primary interest in the past. Emerging contaminants might be more of a problem in the future. So SELDM can be used to model random water quality data, dependent water quality data, and transport curves. And again, for the highway, we can do random water quality data, dependent water quality data to predict something for which there's little data from something that we have a lot of data. And then in the receiving water, we have random, dependent, and transport curves, which are relations between stream flow and concentration that are seen in many basins. All right, great. So now we went over kind of the basic hydrology in SELDM and water quality. Right now, there were questions about the dilution factor analysis and how SELDM does that and why we may want to do that. So I'll go through that fairly quickly. And then what we can do is we can talk about next directions. We might, depending on the time we have left, we might have, I can go through the highway runoff database real quick to show you how to get some data out of that. But I'm thinking that maybe we want another session where people just kind of play with SELDM in parallel, and we kind of go through and do another analysis. I think that should be the focus of our next class. All right, now let's talk about dilution factors, and then we can have a general discussion at the end. So dilution factor analysis. So our learning objectives for this, hopefully we'll explain the concepts of the dilution factor, describe where to find the outputs, discuss use of the dilution factor, and describe a sensitivity analysis that you can do with the dilution factor. So dilution factor, as defined by Driscoll in the original highway runoff model, is a bit backward because a higher dilution factor means there's less dilution. So the dilution factor for a given event is the highway runoff for a given event, the event being I, divided by the highway runoff plus upstream flow. So it's the highway runoff over the downstream flow. So if we're looking at an ephemeral stream that really doesn't start runoff, the dilution factor, if the upstream flow is about 0, then the highway runoff might be 1, right? So the highway runoff would be almost everything in the stream. If you had something like the Mississippi River, your upstream flow is going to be so huge that the highway runoff is going to be infinitesimal, and you're going to have a highway runoff dilution factor of close to 0. As long as you have highway runoff, it's never going to be 0, and as long as you have any upstream storm flow, it's never going to be 1, but it's going to be bounded by, a very small number and 1. So The dilution factors are in we have xxx-df.txt file. So when you run your analyses in SELDM, you can open the tab that will bring you to your output files. So the dilution factors are in the -df file. So it's just the XXX would be your analysis name that's been truncated down to give it. So in this case, we can see that the analysis name was dilution factor 10 imperv, and then the output file is dilution factor 10 imperv-df.txt. And as we've seen when we looked at the output, all the SELDM outputs are tab delimited text file to facilitate use in Excel or in graphing packages so that you can copy and paste the data in to make graphs, do any post-processing statistics. You can sort by values. When SELDM generates it generates it just in storm event value, and it has the annual load accounting year is the next column, and then just the randomly generated percentiles. As you can see in this graph or in this diagram, if you do not have a BMP, your BMP dilution factors are going to equal your highway dilution factors. So it creates the columns, but it just populates them with the same number. Okay, so our example for analysis was done by using data for the USGS stream gauge on Sasko Brook near Southport, Connecticut. The stream flow and water quality data from the gauge at point G were used to do the analysis. So there's an actual water quality monitoring station down here on its Farm Hill Road. So the basin properties for the 8 other sites along the brook and its tributaries were calculated with information and data from the online Connecticut Stream Stats application. The variables shown here are the basin area and the basin lag factor. So if you remember, the basin lag factor is the length divided by the square root of slope. The basin lag factor, so as we progress downstream from A to H, the drainage length increases and the slope decreases, which results in an increasing basin lag factor. The basin lag time and thus the duration of the upstream storm flow increases with area. The following examples are based on the assumption that the highway geometry remains the same, the basin area length and slope are variable, and the hydrologic and water quality data measured at the stream gauge are valid for the upstream and downstream points. So basically what's happening is you're getting, there's kind of 2 competing things, is that you're getting more storm flow for the whole storm, but the duration of concurrent flow may be going down because, you know, the upstream hydrograph is getting longer and longer and longer, whereas the highway hydrograph duration remains the same. So this would be, you know, if you can think, if you're putting in a new highway someplace and you have this important stream here, each of these letters might be like an alternate route across the basin. So you could easily do a dilution factor analysis to see, you know, what might be the worst case scenario. Where would I put this highway crossing that might, you know, have the greatest local adverse effect on the stream? So what we see is increasing drainage area reduces the dilution factor. So what we have here is, again, that probability axis where it's all, you know, the extremes are kind of stretched out. Our dilution factor is on a log scale from 0.00001 to 1. So again, 1 would be 100% highway runoff. 0.1 is 10% highway runoff. 0.01 is 1% highway runoff. So we can see from top to bottom here, we go from that 0.46 square mile basin down to the 9.72 square mile basin. So you can see these different lines are the different dilution factors at these different points. We can see at the maximum dilution factor, what's this, is like 0.2, 0.3, 0.4, 0.5, 0.6, 0.7. So for that smallest basin at this site, the highway runoff is about 70% of the downstream flow. Now, if we move the highway down to this 9.72 square miles, we can see that it's about maybe 25% at the worst case. And we can see that at the highest, in the smallest basin, it goes down to about, what's that? A tenth of our 0.0 or yeah, 0.2% of the downstream flow. And we can see that that's at the largest basin, it's 1 times 10 to the negative 4. I can't walk and chew gum at the same time after 2 presentations here. What we can see that's interesting is kind of up here at the end when you get, you know, between 5 and 9.72 square miles, you're almost doubling the area. But what we're seeing here is the interaction between length and slope is affecting the magnitude of the dilution factors down here, you know, at the high end. But that kind of spreads out when you look at the medians here. So given this, we could see, oh, if we put the highway at each of these crossings, what's our dilution, you know, what's our population of dilution factors are going to be? So, you know, in theory, as you move down the basin, you're going to get more dilution. So dilution factor analyses can also indicate the effectiveness of your BMPs. So this is a case where we're showing dilution factors on a log scale on the vertical axis, and again, the probability scale. So the white line, or it seems to be a line, but it's a bunch of points, is highway runoff. And the light blue line would be highway runoff with a hydrograph extension BMP, hydrograph extension alone. The dark blue line would be a flow reduction BMP. And then the yellow line would be hydrograph extension and flow reduction. So I guess hydrograph extension would be like a pond, like a solid bottom pond that stretches out the hydrograph but does not reduce the volume. The dark blue line might be like, you know, like an infiltration swale where you're not really slowing down the water, but you're infiltrating it as it drains off the site of interest. And then hydrograph extension and flow reduction, let's say that's a swale with check dams. So you're slowing the water and you are infiltrating the water. So we could see that if you could do hydrograph extension and flow reduction, you know, you kind of have a multiplicative increase or decrease in your dilution factors compared to just highway runoff alone. So this is just a hypothetical BMP, but you could run different BMPs and see how those BMPs affect your dilution factor. As we talked in the last class, you know, if you look at the highway runoff database, there's hundreds of compounds that have been detected in highway runoff. I think many more that have been detected in urban runoff. So it's hard to nail down exactly what, you know, any one constituent is going to do, especially since most of the data are for relatively few constituents. But if you can look at your dilution factor, you can see perhaps, you know, how can you improve receiving water quality by using BMPs. The dilution factor is one easy number. It's easy to get your head around the dilution factor versus different chemicals, and you know, you can kind of see what's going on rapidly and without. It's in SELDM. It's easy to simulate a whole bunch of constituents, but you know, you might get different answers for different constituents. So sometimes the dilution factor is kind of the bottom line for conditions of interest. Now, this graph shows that the index flow can have a big effect on dilution factors, and therefore your estimates of the potential effects of runoff on receiving waters. This is a sensitivity analysis to see how the upstream flow specification method affects the results. So the vertical axis is the dilution factor on a logarithmic scale over 5 orders of magnitude, just like we had on the other graphs. The horizontal axis is the probability scale indicating the percentage of storms with dilution factors that equal or exceed a given value. As with the other dilution factor graphs, the white line shows the dilution factors from highway runoff that would occur at the Sasko Brook stream gauge without BMP modification. The 3 other lines demonstrate potential effects of using deterministic upstream flow. So rather than stochastic upstream runoff flow, using these deterministic flow, or use the same flow for every storm. So the other 3 lines demonstrate the potential effects of using these deterministic flows. The red line shows the effect of the assumption that the 7-day, 10-year low flow, the 7Q10, can be used to evaluate stormwater effluent. On average, use of the 7Q10 biases the dilution factor by 190 times the dilution factors calculated with stochastic storm flows. I've seen this and I've heard this where regulators, because they use 7Q10 for wastewater treatment plant, they think, oh, that's the conservative approach for stormwater. Well, it's kind of, it's really a case of apples and oranges, whereas some storms do start at the 7Q10, very few actually start at that value. So, if you're inflating the amount of highway runoff and downstream flows by an order of 190 times, you're going to be building BMPs in a lot of places where perhaps you don't need them, or maybe advanced BMPs in places you don't need where a basic BMP might be sufficient. So similarly, use of the mean annual flow or mean monthly flow biases dilution factors by about 2.6 or 3.8 times the dilution factors compared to stochastic flows. I hate to get into throwing mud balls at high run, although some people might beg to differ, but I believe this is the approach that high run uses. If you see those monthly or annual outputs, they're using the same monthly or annual mean flow to do your highway dilution. So you're overestimating the potential effect of the highway runoff by 2.6 to 3.8 times than if you're getting more realistic stochastic storm flows. So these biases and their effect on downstream concentrations may result in time spent on more detailed analyses. So you can't do like a FONSI or categorical exclusion because you're overestimating the impact of the highway. Often, where there's a potential problem, you have to go and invest a lot in data collection efforts to kind of get a better idea of what's going on at a given site. And kind of the worst case is implementation of mitigation measures at sites where they are not needed. I recommend that people go and look at the 2014 NCHRP report on the long-term costs of BMP analysis. I've done kind of back of the envelope calculations for Massachusetts DOTs, and if they put a BMP at every road stream crossing in Massachusetts, I think the cost of maintaining the BMPs would rise to like half of the DOT budget. That means, they wouldn't be maintaining roads anymore. They'd just be maintaining BMPs if we got to that point. So it's important to get a good answer, but being over conservative really has a lot of effects that, you really want to target available resources to optimize, your bang for the, your bang for the buck. Or all right, so yeah, so these biases and their effect on downstream concentrations may result in time spent on more detailed analysis, investment in data collection efforts, and implementation of mitigation measures at sites where they are not needed, or maybe advanced mitigation measures where maybe basic mitigation measures could be used. Okay, so hopefully after this, we looked at dilution factors are the proportion of highway runoff and downstream flow. You can get that in the file with the DF suffix, and examining the dilution factors gives you a lot of good information without diving deep into the intricacies of water quality. Generally, there's a lot more precipitation and flow data available than water quality data for many constituents. So the dilution factor is a robust way to look at it. And you can quickly use the sensitivity analysis with dilution factors to show the effects of variations in different variables on the potential impact of highway runoff at a given site. Now, the other day, we also talked that, we showed that Sasko Brook example. I think in the Pacific Northwest, they worry about if they, even if they have a highway in the high up in the basin, they worry about what the effect of that might be, downstream where the salmon are. Well, with SELDM, what you could do is you can do a hypothetical analysis where you use your existing site, but you model it as if it's down in the basin. And we could see there that, you can see with the additional dilution that will occur from all the stormwater and base flow inflows between the actual highway site and the actual place where you're worried about a given species of interest. All right. I will stop the recording and we will see and we will take questions.